Alright, so I thought I'd start with a recap of the integration extension 2 topic as a whole. It's a little bit messy, but basically we have 6 main sections of the topic. Some are obviously a lot more prevalent than others in HSC exams. The first thing we did, and I think these are roughly in order of what we did them in class, was a table of standard integrals integrations. I think they're your most basic, just the ones where you can easily manipulate it and sub it into a certain formula, you could say, that's given to you on your table of standard integrals. Next, you have your quadratic denominator questions, and there's a number of options that could happen. And this is mostly where you can use that this mind map here. So basically, I've done a small, doesn't want to move here. So this mind map is all your options if you do have a quadratic denominator. And I've done a small little summary here, including all of those. So knowing, what's the difference, what happens when there's a constant on your numerator, you complete the square. If there's a denominator that can be factorized, we do partial fractions. If you can't factorize a denominator, that's when we do that manipulation method and we get the denominator in the numerator somehow. And otherwise, when you get into the square roots, that's another part, but we did look at them in class, and most of the time it's where you can separate it out. So go back through your notes and look at those. Then you've got integration by parts, that's a big one. Your trig integrals, so remembering your different identities, which you can use as substitutions. Your t substitution, and then, of course, the worst one of all, recurrence relations. Now, I would be, if I were you, making a summary, if you haven't already, on each one of these things with maybe an easy and a hard question. Otherwise, what I thought I would also show you is this document. No, here. This is your formative, okay? So I've just shown you part of it. And basically, I've categorized it into marks here, as you can see: integration by substitution, with quadratic denominator, by parts, and recurrence relations. It doesn't mean you don't need to know the other ones. It just means that those other ones can be further categorized down into one of these 4 within. Now, I have calculated, same as an advanced HSC, you get 1 minute 48 seconds per mark on average, which means if this is out of 29, it's 52 minutes. So I suggest I'd suggest getting the class on time after lunch to give yourself the entire lesson. So what I have done from here is written out, I think, 7 questions here. Yep, 7 questions. Very, very similar to what's in the formative, and I'll give you hints throughout as well. So what you might want to do is pause the video now and maybe give these 2 a go and see if you can do it after you've made your summary, perhaps. Otherwise, I am going to go through them. They're not the exact same, but they are very, very similar. So the first one we're looking at here, straight away we can see, okay, well, we have a quadratic denominator, but we cannot factorize it. And so, okay, well, let's have a look at this mind map. Alright, it is proper because the numerator's degree is smaller. It does not factorize, no. So then it says, look at the numerator. Is the numerator a constant? No. It says, adjust the numerator to contain the derivative of the denominator. Now, it doesn't have to be us so muit as adjusting it. What you can do instead is just separate it. Think about separating it out so that it can be written in as a separate integral. So let's go back to the question. We really could write this as the same thing as, that's the same thing as the integral of x over x squared plus 4 and we're plussing it with 1 over x squared plus 4 dx. Now, technically, we still have done what they said by adjusting the numerator to contain the derivative of the denominator, in this case here. But basically, it doesn't have to just be that. If you can separate it, that's the way I would start by going. Once you can separate, then see if you can now integrate each individual integral. So I could write it as separate integrals altogether. Now, what you can see here, it is pretty obvious we can do each integral individually, because we can say, all right, well, the first one's going to be a log. Actually, well, yes, the first one is going to be a log. And when we can write it as a log, we want it to be 2x on top. So what is x times by? Times is by 2. Flip that upside down. So we will have half log the bottom. Easy. And then we say, okay, this one is not going to be a log because when we differentiate the bottom we have 2x and we can't manipulate the numerator if there's a pronumeral missing. The next option though is think about your table of standard integrals. What do we have here? We have a quadratic denominator. We're looking at tan, and 1 over a squared plus x squared is equal to this term here, and we do have it in that form. Now, here we are. This is really the same thing as in the form of one over x squared plus 2 squared. Now, technically what you should be doing is saying, okay, well, let's u equal x, du over dx equals 1, so du equals dx, make that substitution 1 over u squared plus 2 squared, and then make du, make your substitution. But we did say in class that when you differentiate, if you can get 1, you don't have to do this substitution method. We said in class that lesson, and flick back to your notes, that if you can differentiate and get 1, it's okay to just throw it into your table of standard integrals. But it was when you differentiate, and this might be number 2, that's when you're going to get something like du on 2, and then you'll have to bring a half out, which wouldn't happen if you just substituted into your table of standard integrals. So my point to my story is, remember that when you differentiate whatever you let u equal, if it's 1, then you can see that straight away, you can just throw these values in. And when I say throw them in, looking at your table of standard integrals, a would just be, in this case, 2. So it's as simple as then going, okay, well, it's 1 over a, 10 to the minus 1 of x, which is just x, on 2, and then plus c, because it's indefinite. And there's my answer. So the key thing with using your table of standard integrals is making sure that, you know, there's no underlying substitution that needs to be made that can affect your final answer. Okay? Alright. So there's that one. Let's move on. We say, okay. Alright. Now we say, well, this doesn't have a quadratic denominator. I can't just integrate it using integrations I know from extension 1 and advanced. So the only option I really have is to make a substitution. So let's say, okay, well, what if I let u equal something here? Could be done. Now, not just that, substitution method works if you can see the derivative of the function timesing by that function in some way. So see how we can see straight away that the derivative of this whole denominator really in the brackets would be just x. Sorry, would be 2x. And we have x as our numerator. So there is some sort of manipulation or way that they've written the question that has the derivative involved in it. And when that's the case, it's usually going to be a substitution method. Because you'll soon see now, if I continue du and dx, rearrange to get dx, now make my substitution, so I will get, that's the same thing as the integral of x over u to the power of 7 dx is du on 2x. And what do you know? My x's will cancel, which is just going to give me the integral of u to the power of negative 7 du. And I can go from there. Now, if your x's didn't cancel, one of two things are left. You could rearrange your u substitution up here to get x equals and sub that in. However, sometimes that can make things worse. If you did rearrange this, you'd have u minus 5, the square root of u minus 5 equals x. And so you could sub that in for x. But what I'm saying is, if that's going to make, if you try and do that when your x's don't cancel, and it makes things uglier, then substitution mustn't be the method you're supposed to be using. Basically, your x's should cancel, and if they don't, you should be able to rearrange for x equals and sub that in nicely. But anyway, our x's did cancel here, so it's just a matter of, okay, well, now we can integrate. Add 1 to the power and divide by it, and make my substitution. I could clean this right up and have 6 timesing by, now u is 5 plus x squared all to the power of 6 plus c. And there I have it. My substitution came back and was quite a nice number in the end. Okay, let's keep going. Alright, so we've got a quadratic denominator. Let's have a look at our mind map. Okay, we've got a quadratic denominator and there was a constant on top. So yes, it was proper. No, from memory, that cannot factorize nicely. Okay, so it can't factorize nicely. So is the numerator constant? Yes, complete the square. Alright, so let's go back and complete the square now. Now I want you to be getting faster and faster at this, but okay, let's complete the square. If we do it the long way, it's going to be 1 over x squared minus 4x plus box plus 21 plus, and then we want to even it out, so we need to then minus box. And box is b on 2 all squared. So what do we get? 4. Alright, now sorry, I'm just going to manipulate this question here. Just realized my change to the question needs to be negative here. Okay, let's make that. And you'll soon see why I just did that. Okay, so now completing the square, I'll have 1 over, whole idea is we get a square here, minus 25. And now, once we complete the square, it's in the form of our table of standard integrals, 1 over something squared, plusing with something squared. This isn't working out. I should have checked this. No, let me change the question again. Sorry. Let's go, instead of minus 21, let's do 12. Yep, let's do 12. Sorry. No. Hopeless. 20. 20. Let's do plus 20 instead of 21. Now, hopefully you'll soon see now why I'm doing this, because I'm going to get positive 16. It has to be a positive there. Okay, it needs to be a square number and a positive, so I just had to manipulate the question. So hopefully I haven't lost you, but basically let's make this the question now. And we've completed the square, and what do you know? We get 2 squares, which now coincides with our table of standard integrals of tan, which says that if you have 1 over something squared plus something squared, we get that. Now, like I just said before, if you can see that your substitution of u is going to give you just a positive 1. So, for instance, in your head you'd say, okay, if I did let u equal x minus 2, du on dx equals 1. And as soon as you get that, you don't have to do the formal substitution. We can now plug it straight into our table of standard integrals, which says we do 1 over a, which is 4, tan minus 1 of x over a plus c. And there's my answer. So what do we get? We have a quadratic on the bottom that can't factorise and a constant on top. Complete the square, sub it into your table of standard integrals. Easy. Alright, we've got a quadratic on the bottom that can be factorised because they've told me that. And my numerator is a degree of 1. So as soon as I see that, does the denominator factorise? Use partial fractions. There's my answer. Partial fractions, again, pause the video at any time and give these a go. I'd really like you to. So let's assume you have. We say, well, that's the same thing as the integral of and now, remember the cheat method that I told you never to use, but you can use it to check? I'm going to do that cheat method now so I can just see what I need to get to. If you cover up one of them, okay, and that one you covered up, whatever makes 0, so negative 2 would be the x value, sub in negative 2 into everything else. I get 5 times negative 2, negative 10 plus 1 is negative 9, over negative 3, it's going to give me an answer of 3. And then unfold that one, cross the other one out. The other one to get 0 would be 1, so sub 1 in for x. I'd get 5 plus 1 is 6, and I'm going to have 6 over 3, which is 2. So A and B, I should have answers 3 and 2. So now let's check. Remember, you cannot do that in an exam. You need to show you're working. So now what we do is we multiply up. I get that 5x plus 1 is equal to A, lots of x plus 2, plus B, lots of x minus 1. If we can factorize into the terms, we get 2 simultaneous equations. So we can have something here that A is equal to 5 minus B. So we get 10 minus 2B minus B equals 1 minus 3B equals negative 9. So B equals 3. So therefore A equals 5 minus 3. So A equals 2. Perfect. Just what I knew I needed to get. But I'm not done. I've just found the numerators to be able to split up that. So I know now that that's now the same thing. I'll continue over here. It's the integral of 2 over x minus 1 plus 3 over x plus 2 dx. It'll always just end up a log. From what I've seen on these types, yes, you'll get a log. The derivative at the bottom is not on top, but hopefully you're getting better at your logs, and you know that that's just going to be take the 2 out the front of log the bottom, and the 3 out the front of log the bottom, log the bottom, plus c. Alright, Next one. So I'm looking at this and I'm saying to myself, okay, what can happen from here? What looks like could be the only option I have? Well, let's try substitution. There's nothing else. There's not a quadratic denominator. There's nothing I can use my table of standard integrals with. There's no trig substitution. If all else fails, just do substitution. My substitution, we usually let the ugly thing equal u. The ugly thing is what's under the square root. Now, there are two ways you could do this. I could let u equal the square root of 8 plus x, or let u equal 8 plus x. Now, in my experience, the best thing to do, in my opinion, is to just go with ease. And for me, that's just keeping it as 8 plus x. Once I differentiate that, I get a nice value of 1, so du equals dx. And this is one of those examples I was talking about before, where if I make my substitution now, I get 2x over the square root of u times by du, and my u's don't cancel. My x doesn't cancel. When my x doesn't cancel, I try and rearrange my substitution to get x equals, and this one's quite nice. So that really is now the same thing as 2u minus 16 over the square root of u du. Still not very nice. I've got a u on the top and a u on the bottom. Trying to integrate, that's pretty ugly. So why don't I split it up? That's the same thing as the integral of 2u over u to the power of a half minus the integral of 16 over u to the power of a half du. And this can clean up. U to the power of 1 divided by u to the power of half, we subtract the integral, the indices, so we get 2u to the power of a half minus 16, and I'll just bring the u up to the power of negative a half here. Hopefully you're following. There's nothing too complicated, just manipulating indices. And now I can integrate. So I add 1 to the power and divide by it. So what will I get? 2 timesing by u to the power of 3 on 2, flip and times, minus 16 timesing by, add 1, a half, flip and times, clean it up, 4 on 3 times by the square root of u cubed, minus 32 u square root u plus c, and then make my substitution. I had a substitution of u being 8 plus x, and there I have it. Okay, moral to the story, if all else fails, you don't know where you're going, what to use, make a substitution and see where you go from there. Alright, our favourites. They're not that bad, especially the one I'm putting in your formative. If you can do this and understand this, you should be fine with the one in the formative. Alright, so let's have a look at this. It says if the integration of x to the power of n e to the x is, pardon me, then show that it can also be expressed as the integration being that, and then hence find that. Alright, let's just go back to square one. If I had this question and x had a power, so for instance, if I had this question here, my first option is integration by parts, because there's two functions multiplying by each other, and I know that when that is the case, I can do integration by parts. Now, integration by parts, we said, has this very nice formula, and I remember it by saying other. If you can't remember that, let me just see, here we are. So we have the integral of u v dash is equal to u v minus the integral of v u dash dx. Alright. Now, I'm not integrating this x cubed e to the x part yet because it says hence. I have to show first that in can be represented as this. So let's do integration by parts on x to the power of n, e to the power of x. Think once again, no matter what power x has, we need to name one of these the derivative, v dash, and one of them u. Thinking about which one which. The integral, we can take of both. The derivative, we can take of both. So it's really just a matter of which one's going to be nicer. Well, the integral of e to the x is e to the x. The derivative of e to the x is e to the x. So that one can be either. So then it's just a matter of, well, what's nicer? The derivative of x to the power of n or the integral of x to the power of n? And I would definitely say the derivative of x to the power of n is nicer. Which then leads me to then say, let make this u so I can differentiate it and this be v dash so I can integrate it. And always on the side, I'm going to go with this. And it doesn't matter how good you get at this, always do it. And sub in. So I get an answer of u integral of v times u dash okay. Now I think to myself, alright, I've done my integration by parts. What do I need to do again? I need to show that it can be written as this. And I compare it to what I've got so far. Yeah, I've got that first part down packed. What I'm missing though is n timesing by the integral minus 1. And that's where you should be able to see straight away by looking at this. This is the question exactly. If I take out the n, let me do one more step here. This is exactly the question that we got given. But instead of in, it's in minus 1. Which is then why they get the very next line of that. And I've proved it. Really easy. Now that I've done that, it wants me to find x cubed e to the x. So, that is going to be I3 because n is 3, so let's sub it in. So I get that's x cubed e to the x minus 3 lots of I2. And this is that fun part that we all love. Now I sub in 2 into my formula to find the integral, which is this one. So that's x2 ex minus 2 lots of I1. So now I do it again, subbing into I1. Sub 1 in, I get x e to the x minus 1 lots of I0. Now remember I said in class, I0 just throw back into your original. My original is as in my original question, okay? So x to the power of n e to the x is going to be then the integral of x to the power of 0, which is 1. So just the integral of e to the x dx. How many brackets do I need there? Okay, now the integral of e to the x is just e to the x, so it cleans up pretty nice, and I'm going to expand out my brackets here. Then it'll become plus 6 x e to the x. Then that minus will become minus 6. Integral of e to the x is e to the x plus c because I did an integral. And we did this one in class because we can factorize out the e to the x and we'll get x cubed minus 3x squared plus 6x minus 6 plus c. And there is my integral. Alright, moving on. Now, I want you to give this one a go, and not just a go with tan cubed. I want you to, as a big hint for the formative, give this question a go with cos cubed and sine cubed as well. Know how to do powers of trig. Okay, so I'll do tan cubed and I will show you how this one is done. But yes, my big hint for the formative is to know how to do your powers of sine and cos also. Alright, let's have a look at this. Now, I can separate this, and we did one in class like this, oh, that's shocking, as the same thing as tan x timesing by tan squared x. And I know that tan squared x, I could make even simpler, is tan x timesing by sec squared x minus 1. And if I expand that, I get tan x sec squared x minus tan x dx. Now what I have here is, I'll do it in a different colour to show just my working for this section. Integration by parts. I have two functions multiplying, or two equations multiplying. Which one should I call u and v dash? Well, I can take the integral of both, yes. I can differentiate tan, but can I differentiate sec squared? Let's look at this. No. If I'm looking at the right hand side to get back to that, I can't differentiate sec squared. So there's my answer. Sec squared needs to then be something that I need to integrate, so I'll call that v dash. And tan is u. Alright, so my uv dash is equal to other uv minus the integral at uv dash vu dash dx. Alright, so u is equal to tan x. I know that u dash is equal to sec squared x. V dash is equal to sec squared x, and v is equal to tan x. Make my substitution. I want v becomes tan squared x, because there's two tans, minus the integral of v u dash. And I get to this point and go, okay, I've done my integration by substitution, but, sorry, my integration by parts, but what do I have here? Have a look and see if you can work it out. What do I have here? Hopefully you can actually recognize, but what you have there is the original question, okay, which was this underlined part here. Okay, so if we let that, what we were just doing, integration by parts, be I, let's just call it I, not IN, I, then this is the integral of I. Now I have the integral of I is equal to tan squared x minus I. So I bring that I over, I get two i's is equal to tan squared x. So 1i is equal to a half tan squared x. And what do you know? Works out nicely. But remember, this is only the blue part for the blue underline part. Bring back down the original question. The original question now says, okay, you wanted the integral of tan x sec squared x minus tan x. Now, as a side note, tan x is sine over cos, so that's really the same thing as negative sine x over cos x. And what do you know, the derivative of the bottom is on top. We've seen that before. So I know the integral of this part is what I just worked out, so it's a half tan squared x. And I now know that the integral of this second part here is a log, because the derivative of the bottom is on top. It's a negative log of the bottom. Now you can't log a negative, and cos can have negative values, so what you should actually have here are absolute value signs. And then plus c. And there's my answer. So have a go at that question with sine and cos as a power as well. Okay, so I'm fairly confident we are finished. There's nothing else I needed to say. Cool, alright. So, like I said, this video is an idea of what to expect. I wouldn't just be knowing this video, but if you know this video inside out and you can recompute any question similar to these with the same ideas, you will be fine for the formative, but I would be doing some extra things and definitely making a summary on these main parts that I talked about here.